Hello viewers, in today's session we are going to discuss some important problems related to finding out the higher order derivatives of functions. Right, so here we'll solve some important problems in which the higher order derivatives are involved. Right, so let us take the problems one by one. So let us first take this problem in which we are given e raised to 100 x square plus y is equal to x raised to 200. Then we have to show that x cube times the third derivative of y with respect to x is equal to 400. So here we are given this expression in which the power of e is 100x square plus y, and the right hand side is x raised to 200, and we have to show that x cube times the third derivative of y with respect to x. So we can also write x cube times d3y over dx3 is equal to 400. So here this derivative is known as the higher order derivative, and here the third order derivative is involved. So now to arrive at this result, what we will do, we'll take help of logarithms and we'll take the natural log of both sides. So we have natural log of e raised to 100 x square plus y is equal to the natural log of x raised to 200. So here we can make use of this property of log, that is log of a raised to m is m times the natural log of a. So here we have 100 x square plus y, and then we have log of e, and here we have 200 log of x, and log of e is equal to 1. So we have 100x square plus y is equal to 200 times natural log of x. So now let us differentiate both sides with respect to x. So we can now write d by dx of 100x square plus y is equal to d by dx of 200 times log of x. So here the derivative of x square is 2x, and here we have dy over dx, and here we have 200 because 200 is a constant, and here log of x. So the derivative of log of x is 1 over x. So we have 200x plus dy over dx is equal to 200 over x. And now we can take this term to the right hand side. So we have 200x 200 over x minus 200x, and this is 200, taking 200 common, we have 1 over x minus x. So the first derivative is given by this expression. So now to get the second order derivative, let us differentiate both sides with respect to x. So we have d by dx of dy over dx, and here we have 200 and d by dx of 1 over x minus x. So this is the second order derivative d2y over dx2, and here we have 200. The derivative of 1 over x is minus 1 over x square, right, and the derivative of x is 1. So this is the expression for second order derivative. So now let us differentiate both sides to get the third derivative. So we have d by dx, and here d2y over dx2, and here we have d by dx of 200 minus 1 over x square minus 1. So this becomes d3y over dx3. that is the third order derivative. And here we have 200, taking 200 outside this derivative operator, we have dy dx of minus 1 over x square minus 1. So this is 200, and the derivative of 1 over x square is given by minus 2 over x cube, right? And the derivative of 1 is 0. So now the derivative of minus 1 over x square minus 1 is given by minus 2 over x cube, right? So the derivative of 1 over x square can be written as d by dx of x raised to minus 2. So this is minus 2 times x raised to minus 2 minus 1. So this is minus 2 times x raised to minus 3. So this is minus 2 over x cube, right? So now the third derivative is equal to 200, and here minus times minus is positive, so we have 2 over x cube, that is equal to 400. 200 times 2 is 400, and this is 400 over x cube. So now we have the third derivative, that is y triple prime. The notation for this is y triple prime, and here we have 400 over x cube. Now multiplying both sides by x cube, we have x cube times y triple prime is equal to 400. And this is the result which we have to prove. So now let us take this second problem, in which we are given that y is equal to x cube times log of x, and we have to show that x times the fourth derivative of y with respect to x is equal to 6, right? So we'll start with this expression, y is equal to x cube over log x, and we have to find the fourth derivative of y with respect to x to get this result. So now differentiating both sides with respect to x, we have dy over dx is equal to d by dx of x cube log x. And here to get the derivative of x cube log x, we'll make use of the product rule by taking x cube as the function u, and log of x as the function v. So we have d by dx of u times v, and the product rule for differentiation is u dv over dx, and then v and du over dx, right? Okay, so here we have u as x cube, so we have x cube, then derivative of log x, and then we have log x and derivative of x cube, right? So this is x cube, the derivative of log x is 1 over x, and here we have log x times the derivative of x cube is 3x square. So here this x and this x get cancelled, so we are left with x square, and here we have 3x square and log of x. So the first derivative of y with respect to x is given by this equation. So now differentiating both sides with respect to x to get the second derivative, we have d by dx of dy over dx, and here we have d by dx of x square plus 3 times the derivative of x square log x. So this is the second derivative, d2y over dx2, and here the derivative of x square is 2x, and here we have 3, and again applying the product rule, taking x square as u and log x as v, we have x square, then the derivative of log x is 1 over x, and then we have log x, and derivative of x square is 2x. So this is 2x plus 3, and here x and x get cancelled. We are left with x, and then we have 2x log of x, and this is 2x plus multiplying these two terms by 3, we have 3x plus 6x log of x, so this is 5x, 2x plus 3x, 5x, and here we have 6x log of x. So the second derivative is given by this expression. So now differentiating again both sides with respect to x, we have dy dx of d2y over dx2, and here we have the derivative of 5x plus the derivative of 6x log of x. So here we can now write the third derivative d3y over dx3, and here we have 5 being a constant. We have the derivative of x with respect to x is 1. Here we can take 6 outside, the derivative of x log x. So now we have 5 plus 6 times the derivative of x log x. So taking again using the product rule, taking x as u and log as v, we have x, derivative of log x is 1 over x, then log x, and derivative of x is 1. So now this is 5 plus 6, and here x and x get cancelled. We are left with 1 plus log of x. So this is 5 plus 6 times 1 is 6 plus 6 log x. So this is 11. 5 plus 6 is 11. 11 plus 6 log of x, right? The third derivative is given by here 11 plus 6 times log of x, right? Now here we wish to find out the fourth derivative. So again differentiating both sides with respect to x, we have d by dx of d3y over dx3, and here the derivative of 11 is 0 because 11 is a constant, and here we have 6 times the derivative of log of x. So here we have the notation for fourth derivative as d4y over dx4, and here we have 6 times the derivative of log x is 1 over x, so this is 6 over x, right? So multiplying both sides by x, we have now x times d4y over dx4 is equal to 6, and this is the required result which is to be proved. Now consider this third problem in which we are given that y 10x is equal to 1, and we have to prove that d2y over dx2 plus 2y dy over dx is equal to 0, right? So from this relation will start, and we are given that y times 10x is equal to 1. So we can rewrite this expression as y is equal to 1 over 10x, that is equal to cot x, right? So now differentiating both sides with respect to x, we have dy over dx is equal to d by dx of cot x, and from the standard result we know that the derivative of cot x is minus cosec square x, right? And from trigonometry we know an important identity connecting the two functions cot theta and cosec theta as 1 plus cot square theta is equal to cosec square theta. So here we can now write cosec square x as 1 plus cot square x. And for cot x, we can write y. So we have minus 1 plus y square, because cot x is equal to y. So we have this result, that is dy over dx is equal to minus 1 minus y square. So taking these two terms to the left hand side, we have dy over dx plus y square plus 1 is equal to 0, right? So now differentiating both sides with respect to x, we can now write d by dx of dy over dx plus y square plus 1 is equal to 0, because the derivative of 0 is 0. So now differentiating term by term, the first one is d by dx of dy over dx, and then we have d by dx of y square, and here the derivative of 1 with respect to x is 0, because 1 is a constant and the derivative of a constant is 0. So now d by dx of dy over dx is d2y over dx2, and the derivative of y square with respect to x is given by 2y dy over dx, and this is equal to 0, right? So here the derivative of y square with respect to x is calculated as follows, that is d by dy of y square. So first we differentiate y square with respect to y, and then by chain rule we have dy over dx. So here we can make use of the chain rule, that is d by dy of y raised to n is ny raised to n minus 1. So here we have 2y, y square, the derivative of y square is 2y, and then by chain rule we have dy over dx. So here we have 2y dy over dx. So d2y over dx2 plus 2y dy over dx is equal to 0. So this is the result which is to be proved. So now let us consider this fourth problem. This is also a very important problem, and we have to find the third derivative, that is d3y over dx3 at x is equal to 1 if y is equal to log of x cube over e raised to 4. Right. So here we are considering the natural log, and we are using the notation log instead of ln. Right. So we can also write this relation as ln x cube over e raised to 4. Right. So first we have to find the third derivative of y with respect to x, and then we'll take x is equal to 1. So now we have y is equal to natural log of x cube over e raised to 4. So here we can make use of this property of log, that is log of a over b is log of a minus log of b. So we can now write y is equal to log of x cube minus a log of e raised to 4. So this is y, and again using the properties of log, log of a raised to say m is m times log of a. So here we have 3 times log of x, and here we have 4 times log of e. Now the natural log of e is 1, so we have y is equal to 3 times log of x minus 4 times 1. So y is 3 log x minus 4. Right. So the given relation y is equal to log of x cube over e raised to 4 can also be written in this form. So now differentiating both sides, with respect to x, we have dy over dx is equal to 3 times the derivative of log x, and the derivative of 4 being a constant is 0. So we have 3 times 1 over x, that is 3 over x. The derivative of log x with respect to x is 1 over x. So the first derivative is equal to 3 over x. Now the second derivative is given by differentiating both sides with respect to x. So we have 3 times the derivative of 1 over x. So this is 3, the derivative of x raised to minus 1, and using the power rule for differentiation, that is nx n minus 1, we have 3 times minus 1 over x square, right? So the second derivative d2y over dx2 is given by minus 3 over x square. Now to get the third derivative, we can differentiate both sides with respect to x. So we have d by dx of d2y over dx2, and here we have minus 3 times the derivative of 1 over x square. So this is the notation for the third derivative, d3y over dx3, and here we have d by dx of x raised to minus 2. So again, using this power rule here, we have minus 3 and we have minus 2 over x raised to 3, right? So the derivative of x raised to minus 2 is minus 2 over x cube. That is multiplying both these quantities, we have minus minus plus, so we have 6 over x cube. So the third derivative is given by a y triple prime. The notation for the third derivative may also be used, this notation. So we have 6 over x cube. Now we have to find the value of third derivative at x is equal to 1. So taking x is equal to 1 over here, the value of the third derivative at x is equal to 1 is given by 6 over 1 cube. So this is 6 over 1, because 1 cube is 1, that is equal to 6, right? So the third derivative at x is equal to 1 when y is defined like this is equal to 6.